Hi, hello everybody. So this is the video dealing with exponential and log equations. This is topic 5 on our syllabus, and I decided to break it into two parts. So the first part, I am going to go over exponential equations. So I called it part A. And in the next video, which I call part B, we're going to go over logarithmic equations. Okay, so this is assuming that we already went over in class, and we did over 9.3, 9.4, the first two sections in our course, because we're going to need the basic properties. And right here, 9.3, 9.4, the basic properties dealing with exponential equations and log equations. Exponential equations are pretty straightforward, but the log equations, we will need to know a couple basic things. In any event, so exponential equations. So these are equations where the variable, the x, the unknown variable, usually x, but it could be y, it's in the exponent. So here are some of the examples of exponential equations. And notice that here is the variable x is in the exponent. It's no longer, for example, as a quadratic equation, x squared, right? The variable is in the exponent. 3 to the x plus 1. So this is an exponential equation. Or 2e to the 2x minus 7 equals 12. E is a special base. We'll discuss this. We discussed it before already in 9.3, 9.4. We'll discuss it some more here in when we do part B. Here is a typical exponential equation where both bases are the same. And here where both bases are different. Okay, so these are basic examples. Now, the two basic techniques to solve exponential equations are here. The first case is either where the bases are equal or then they can be made equal to each other. And we'll see that case. So this is a case similar to example 2. And the other case is where the bases are different and they cannot be made equal no matter what. So this is the example, for example, number 5. Okay, there's only two techniques. I'm going to show you how to do both. This is usually the easier case, but this is not much harder than that. Okay, so let's take a look. I'm going to show you the procedure first, how to do when the bases are either equal or they can be made equal to each other. Okay, so here is problem 28.1. Let's take a look at the first problem where I have 3 to the x equals 81. So it looks like the bases are not equal, right? This is a 3 and this is 81. However, the 81 can be made into a base 3. And this is what we have to do. So we turn 81 into something with the same base as the number on the left. Once the bases are equal, so that's the first technique. If the bases are equal or when they become equal, we can just eliminate the bases. So the only thing that we need to solve, in this case, there's nothing to solve, is x equals 4. So it's like you're crossing the two bases out, and the only thing that's left are the two exponents. Look at the second case. 2 to the x equals radical 2. They don't look the same. I have a base 2 here, and I have a base radical 2. But the radical 2, if you remember, is, as you see here, 2 raised to the 1/2. And now the bases are equal. So we just cross or cancel those two number 2's, and I end up with x equals 1/2. There's nothing more to the problem. Same thing with C. I have 5x plus 1 equals 1/5. We turn this number into an exponential number. Right? If you remember properties of exponents, 1/5 is 5 to the minus 1. And now the bases are equal. I have a 5 here and I have a 5 there, so they cancel each other out. I am left with the exponents on the left and the -1 exponent on the right. So x plus 1 equals -1, and we can solve that by subtracting 1 on both sides, and I end up with x equals -2. Okay, so these problems are pretty straightforward. If the bases are not equal and they cannot be made equal, for example, in all of these cases, the bases did not look equal, but we were able to turn 81, we were able to turn the radical 2, we were able to turn 1/5 into the bases on the left side. In these cases here, they won't be able to. There's no way that I can turn a 5 into something that has a base of 2. So when that happens, the technique is we are going to take the log of both sides, and the log will have a base of the number where the exponent is, where the variable is. So in this case, the 5 and 2 are different bases. The 5 cannot be made into a 2. So I need to take log of both sides. Well, log of what base? Well, since the variable is on the left side, I am going to use this number as my base. So I'm going to take log base 2 of both sides. And when I do, I end up with x on the left, because the log base 2 and this number 2 will cancel each other out. I will show you in an example when I do it. And the right side, I will have log base 2 of 5, which then can be solved by a calculator approach. Okay, so this on the calculator will yield this final answer. Same thing for the B problem. Bases 4 and 13 are different. 13 cannot be made into something with a 4. I will take a log of both sides. Since the variable is here, I will take log base 4 of both sides. When I do that, the log base 4 and this 4 will cancel each other out. On the left, I will only have 3x plus 1. On the right, I will have log base 4 of 13. Then all I have to do is solve the simpler equation. Subtract 1 on both sides, divide both sides by 3. This is in essence my answer. All I have to do is use the calculator to find out what log base 4 of 13 is. I can subtract 1, I can divide by 3, and now I have my answer. And similarly with C, but notice with C first, before I do anything, I have to divide both sides by 5. So we proceed by dividing both sides by 5. Then this base is obviously different from that base. I will take the log of both sides using this number because the variable is on this side. On the left side, this 123 will cancel with my log base 123. And I will have this expression on the right. Divide both sides by 4, evaluate what this number is using the calculator, and we'll get our answer. Okay, so this is the technique. If the bases are equal or they can be made equal, we'll use this first approach. Very straightforward, we'll just cancel the base. If the bases cannot be made equal, such as these examples, we will employ the log of both sides technique. Okay, so let's do, I am going to do some of the problems in here, and I already have the problems for us to do. Let's do 28.3 first. And I already copied the problems in a piece of paper so that we don't take too long. All of these questions will be labeled under solve the equation. They may be stated as solve the exponential equation or just solve the equation. So in this case, the problem is 49 to the x equals 7. Notice the bases are not the same. However, it is possible to turn this 49 into something that has a base of 7. And what is that? Well, I know that 7 squared is 49. So I'm going to replace the 49 with 7 squared. So this is what I have. This is my step one. And then I apply the properties of properties of exponential expressions here. And I have 7 to the 2x equals 7. The bases are the same now. And remember, there's an invisible 1 right here, even though we don't see it. Since the bases are the same, they will get canceled. I am only left with the exponent. And now I have to solve the simple equation, which is 2x equals 1. Obviously, I divide both sides by 2. And I end up with x equals 1/2. This is all I have to do. This is the end of the problem. And sure enough, if you check back, 49 raised to the 1/2 is equals 7 because 49 to the 1/2 is the square root of 49. Okay, so that's the first problem. How about, let's do 28.6, and I already wrote the problem here. Again, solve the equation. I'm just going to write solve now to go a little faster. Solve, and we mean solve the exponential equation. And equal to 10. All right, so this is an exponential equation because I see the exponent here has a variable x. So the very first thing I do is I must isolate the exponent on the left side, the expression with the exponent, which means I have to divide both sides by 5 to begin with. So this 5 cannot be here. On the left side, I am left with 4, 2x plus 3, and now I have 10 divided by 5, 2. The bases don't look the same, but I can convert a 4 into something that has a base of 2. And what is it? Well, we know that 2 squared is 4. So I am going to replace the 4 with 2 squared. And here is my 2x plus 3 over here equals 2. I now apply the properties of exponents. And remember, this is in parentheses. So the 2 bases will cancel. This 2 will cancel with that 2, but just keep in mind, there's an invisible 1 over here. Whenever you don't see an exponent, there's an invisible 1. So 2 times 2x, 2 times 3, and here's my 1 on the other side. And now notice all I have to do is solve this simple linear equation. So minus 6 on both sides. Okay, so I end up with 4, these 2 cancel, equals -5, and divide both sides by 5, and I have this. I'm sorry, divide both sides by 4, and I have this. And this is my final answer, as you can see over here. Okay, these problems are very straightforward when we can convert one base to the other. All right, so these are 2 problems dealing with bases that are either the same or can be made the same. What if we have a situation where they cannot be made the same? So let's take a look at 28.4. So it's 6 to the x equals 18. Okay, so here is another problem. And there's no way that I can turn the number 18 into something that has a base of 6. And you can even try. 6 to the 1 is 6. 6 squared is already 36. So there's no way that I can get 18. Okay, so what do we do? Well, the only other option is I have to now take the log of both sides. This is the second technique. I look where the variable is, and I am going to take the log of both sides, this base. Okay. And I am writing the whole problem out so that you can see that once you have the base equals the base of the log equals to the base of the number where your variable is are equal, they cancel each other out. And I'm left with the exponent. So this is my answer for this problem. Now I would normally accept this is if on the final we required to do more, there is a special formula to simplify this if your calculator doesn't do it. The formula is log base 10 of this number over log base 10 of that number. And this, we can do it on the calculator fairly easier, and I'm going to show you now how to do it. Okay, so here is my log base 10. So I'm going to say log 18 divided by log 6. And this is the answer, 1.613, approximately 1.613. All right, and this is the answer for this problem. So the bases are not the same. They cannot be made to be the same. So the second technique is you're going to take the log of both sides, as I did over here. And the log is going to be the log using the base of the number where your exponent is. Okay, so don't confuse. Note, if the problem was 18 to the x equals 6, I would then take log base 18 of both sides. Okay, because the variable x is attached to the number 18. So now the 18s will cancel, and I'm left with this, which is very different from that over here. So this is, I'm not going to do it, but this is log base 10 of 6 over log base 10 of 18. Okay, so let's do one more. And yeah, you can stop the video, obviously, if you have to take a look at some of these problems in more detail. So here's another one, solve 28.7, e to the x plus 2 equals 8. Okay, the very first thing we do is we isolate the expression where the variable is, which means that this 2 cannot be here. So we'll subtract 2 on both sides. I am left with 2e to the x equals 6. E is just a special number that is a little more than 2 and a little less than 3. So it's approximately 2.1728. Okay, we don't need to remember this number because the calculator knows exactly what this number is. We cannot turn this number 6 into e. So what do? We are going to take the log of both sides. But log of what base? We're going to take the log of e. Okay, both sides. Now, normally, as we said before, we don't usually write log base e. When it's base e, we write natural log. But you can write it this way. This is fine. I'll read it both ways. Okay, so natural log of 6. This e will cancel with that e. I am left with x on the left side. And all I have to do is let the calculator evaluate what natural log of 6 is. So I'm going to take a look at the calculator now. This is log base 10. The ln is log base e. So this is the one you have to click, 6. And we get 1.79 approximately, if it's 2 decimals. 1.79. Okay. All right, so this is good. So these are some of the basic properties that we use to solve these exponential equations. Two basic properties, as we mentioned before, if the bases are equal or can be made equal, then we just cancel the bases and we solve the exponent. If the bases are different and cannot be made equal, then we are going to take the log of both sides, as I showed here in the video. But you must first isolate the expression with the log. Okay, so this is the first part, exponential equations. And in another video, I will show you the log equations.